Okay, next lesson now. Come on. Amjad. Amjad! Get back to your seat. Troublemaker.
Like a baby.
Huh? Like a baby? What?
The word you just not just say like get back to your like kindergarten.
Yeah, like kindergarten, yeah. Kindergarten, you know. Put your finger on your lip and listen to the teacher. Alright, so you need to give them something? Hot off the press? Who's this for?
This, yeah.
I actually already I read it also for her.
Wait, hang on. Wait, come back here. You're using your credits for them.
No, I've been stuck in right.
Her credits?
Yeah. Does anybody need this form or is that I have 2 copies to go.
Can you put that back in and get the credits back?
No. We'll
Okay, next page. Now, so what we're going to look at now, the process of first principles, as you can see, is a very long process in order to calculate the derivative. In fact, there were some quick, simple rules to calculate the derivative. So what I'll do is, I won't give you the proof of all of the rules, but I'll show you the proof of one of the rules. And then I'll just list off what all the rules are. So firstly, we want to find a general formula. We want to find a general formula to calculate the derivative of x to a power. Okay? So let's just go ahead normally with first principles. So you get f x plus h would equal x plus h power n. And then, if you think back, this is nc0 xn plus nc1 xn minus 1 h plus nc2 xn minus 2 h squared, etc. This we did in binomial expansion. So then, using the rule, delta y over delta x would equal that whole thing minus xn plus nc2 xn minus 2 h squared, etc. minus xn. All over, close enough, h. Now, if you look here, notice what happens. NC0, what's that? Well, what's the first one in the triangle? It's always 1, isn't it? So that's gone. And then xn minus xn, that's gone. And then divide everything by h. So h divided by h, it's gone. H squared divided by h, h. So anyways, after cancelling and simplifying, you'd be left with this. nc1 xn minus 1 plus nc2 xn minus 2 h plus nc3 xn minus 3 h squared, etc. Now, how do I change from secant to tangent? Make h0. So you'd end up with this. Where's my, they're gone. dy dx, well, they're all gone because they're all 0, is equal to nc1 xn minus 1. Now, who recalls the definition of the c function? It uses factorials, remember? So nc1 is, anyone remember? N factorial over n minus 1 factorial times, yeah, which in this case, 1. factorial, because that's it there. Now, times xn minus 1. Now, what is the definition of n factorial? It's n times n minus 1 times n minus 2, etc. all over. And what about n minus 1 factorial? That's n minus 1, and then what's before that? No, you're going decreasing. So minus 1, so n minus 2, etc. Decrease, minus 1. Now what happens here? A lot of stuff cancels, doesn't it? So you're left with dy dx equals n x n minus 1. So flicking to the left for the moment. If y is equal to xn, then its derivative is nxn minus 1, which can be summed up as a sentence. So when you have x with a power, what you do is you bring the power down in front and you take 1 away from the power, minus 1 to the power. So for example, yes? What do you need? No, it's alright. It's fine. If you're interested, write it down. I don't know actually. Yes?
The last one, right?
Yep. Well, I'm going to put all the formulas in a table, okay? So don't worry about that. So let me show you how to use this formula. So if we just look at the moment, yeah, let's take 1D for example, on the previous page, on page 77. So what is 1D? It was minus x cubed. Look up. This was 1D on the previous lesson. I think I did, that was the first one I did for you, isn't it? And what was the derivative there? What was my answer for that? Minus 3x squared. If I use this rule, the rule says put the power in front and take 1 from the power. So if I put the power in front, I get 3x, and if I take 1 from the power, squared. So you see it's a very quick way to calculate the derivative. Yeah, sorry, minus 3. The minus is the point. So it'll be minus 3x squared. Now, I'm going to not make a change in my use of language, but just to expand it, okay? The word derivative noun means slope of tangent. But you can also use it as a verb, the verb being differentiate. And what differentiate means as a verb is to take something like x cubed and calculate the slope of its tangent, i.e. change it to 3x squared. So differentiate is the verb, meaning to find the slope of the tangent, normally by using quick rules. So one more time, differentiate, verb, meaning find the derivative by usually using quick rules. Right? We're happy? Oh, we're so happy. So what we'll do now is, I've just proven one rule, although it's not quite suitable to give you all the proofs now because it requires stuff from semester 2. So what I'll do is I'll just give you the table of rules. So that's the first rule on the table. Now in fact we can make the second rule very quickly from it. So suppose we have, example here, a constant like the number 4. If I want to write that as a power, it would actually be for x power 0, because x power 0 is 1. So now if I use my quick rule, the 0 comes down in front, and when you multiply by 0, 0. So in other words, if there is no x, then there is no derivative. A derivative is 0. So derivatives of constants always become 0. So derivative of 5 squared plus a million, 0, because there's no x in it, it's a constant. So that's the second rule. Okay, so I'll give them to you now in table 4. And this table is in the formula book. And just as well, this means the original, and then this means the derivative. But just so you know, there's another way you can write it, another symbol. You can also use this symbol. And then here we use y, but of course you could also use f if you want. And if you use f, then instead here you would have to use f with a little dash, okay? So I sometimes switch between the two. So you either go y and dy dx, or you can write f and then f with a little dash here. Anyways, that's not, just so you know that, okay? So I'll stick to dy dx for the moment. Okay, so the first rule says if you have xn, its derivative is nx to the n minus 1. Secondly, if you have a constant, its derivative is 0. Also, if you had a constant times x, what do you think that would be here? It'd just be the c. Now, if you think about it, that makes a lot of sense. Because the graph y equals cx. What type of graph is y equals cx? The name of this? No? Yeah, y equals cx is linear. And what does the number in front of the x represent? The n. And what is the n? The gradient, the slope. So it should not be surprising that the slope of the tangent for cx is c. Should not be surprising. Right? Andy, is that surprising or not? Right, anyways. Now, this one here. Sin x, derivative, cos x. Cos x, derivative, minus sin x. E to the nx, derivative ne nx. And if there's no n, or if n is 1, you have this very important result. Derivative of ex. Pause and let me tell you. This is the reason e is so important, and it's the reason e is the number that it is. Only e to the power of x will be its own derivative. No other function is like this. There is never any other function except for ex that remains unchanged after you differentiate. So we said e is 2.718. If it was a different number, this would not be true. And again, unfortunately, the proof is not suitable for semester 1. Muna? Yes? Yes, question? I'm not finished. I'm continuing. Yeah, don't worry. I'll do tan now in a minute. Don't worry. So ex is special because it is its own derivative. Okay. Now, Muna, tan x, its derivative, 1 over cos squared x. And then finally, well, I'll zoom out, don't worry. log ax plus b, its derivative is a over ax plus b. And of course, normally it's common to see b as 0 and a as 1. So in that situation, you get a much nicer result. Derivative of log x will be 1 over x. So this is in the formula book. It's a table of derivatives, and really it's a matter of just using the table. So I'll do a couple of examples now. Yes?
Cosine squared or cosine x squared?
Cost squared x. The e power nx, so the nx is superscript, and then here
like way down the last one. Yeah.
e.
Yeah.
I'm so sorry, that it's not an e. Important table. Huh?
No rules for logs.
Log?
Yeah.
What do you mean?
I mean, we are only using length.
Oh, you mean for a different base? No, we don't do that in this semester. It's always going to be base E. Yeah. So it'll only be this type of log. Okay. Let's have a look at some examples. So, to start with, maybe I'll go across. Let's go with a nice common blue. So these are my own examples, okay? So x squared plus 5x plus 1. So, the rule says you bring the power down and you take 1 from the power. 5x would become 5, and constant?
0.
Sure. So the answer is 2x plus 5. Another example? ax squared plus bx plus c. We take the 2 down, so what do we get? Here's another example. 2ax power 1 plus 0. What about if I do this one next? 4x plus e to the 2x. So 4x from the table is 4. And then what happens with e and a power? That 2 comes down in the front. But don't make this common mistake. With e's, the power stays the same. If you look at the table. See? There's no minus 1 in the power. It's a common mistake. Don't do that. Now let's look at slightly more difficult ones now.
Is that 2x dash?
2x power 1.
Can you do something?
I will, yes. The next example I was going to do is 1 over square root x. Okay? I know what I'm doing. I really do. I really know what I'm doing, okay? You have very little faith in me. You know? Yeah.
Just I will give you mine.
No, it's not necessary, but thank you.
Is there something up on 2?
The original question just. Alright, next I will do 1 over square root x. Is acceptable to you?
Yeah.
Yes? Well, I'm going to go down here. Now, the problem with this is before we even start, we have to write it as a power. So firstly, I should change it into 1 over x power a half. And then, yes, because it's in the denominator, I can bring it to the numerator by changing the power to minus a half. You could have done that in one step if you like, okay? You could have gone from there to there in one step. It's okay. Now I can use my rule. So what does my rule say? Well, the rule is you bring the power down and then you minus 1 from the power. And then that's the answer. If you like, you can write the answer in this form. Which is the same thing, of course. Problem? Did you write that down, Andy? All right. So really, the examples I've done for you cover number 1 and number 2. Number 2, there's no difference, okay? The only thing that's different in number 2 is I just want to show you different notation. So if we look here, you see in 2a, see in 2a, look at 2a. When you write d over dx in front of something, think of that as a verb. It means differentiate what's inside the brackets. So you should highlight that, d over dx. And it's like a verb, meaning differentiating inside. And likewise, you see in number 2b, 2b, next one, 2b. Yeah. You see there's a little tick at the end, prime or dash. That means differentiate what's inside of this bracket. In other words, the same thing. Huh? Somebody tell me, please. Come on. Who can tell me what does differentiate mean? Thank you, Amro. How nicely put. Yes, as Amro puts it nicely, it is what I am doing. Yes. Differentiate is a verb. What is the noun? Derivative. So differentiate is the verb. It means to find the derivative. Right, yes. See, there's so many variations. There's derivative, differential, differentiate. I'm trying to keep it simple for you. So at a simple level, derivative, noun, differentiate, verb. But then there's also differential, differentiation, and
different.
What's different?
The different is the same thing. Is a different, this one is the same thing.
Differentiation is the same thing. Yeah. Okay. What's wrong? I can't believe you admit that so briefly.
He's asking about DVD.
That'll be next semester. This is product quotient and chain rule. Next semester. Now, you can wait till next semester. Let's take care of this semester first. Now, I'll do, so 1 and 2 I've done, so let me do one from number 3. So, just 3a as an example. They're all the same difficulty. There, super zoom in. Oh, no. Right. D, okay. So you have 9x plus y minus 3 equals 0. Now, away. Now, this one here, I want the derivative. But what's the problem with this one, so to speak? Yeah, but what exactly though? Two unknowns. But remember, y is like the function. It's like the original. So in fact, all you have to do here is rewrite this as y equals minus 9x plus 3. So what does dy dx equal?
9.
Minus 9. Now also I ask you in the question, what is dx dy? Now just think for a moment, okay? When you have dy dx, y is in the numerator, x is in the denominator. That is actually important because it tells you that y is the function and x is the variable. Okay? But if I ask you for dx dy, that means I want x to be the function and y to be the variable. So before you find that, what you have to do then is find what x equals. So here you would get x equals 1 over 9y with a minus plus 1 over 3. So I promise you, if you rearrange your first equation, you can get x equals minus 1 over 9 plus 1 over 3. So in this case, the x is the function and the y is the variable. So when you differentiate, you pretend like the y is the x and vice versa. So here you would say dx dy would equal minus 1 over 9. And what's extremely important here is that if you look at my two answers, dy dx is equal to minus 9 and dx dy equals minus 1 over 9, do you think that was an accident or will that always be the case? What do you think? It will always be the case. So in fact, if I give you dy dx and if I say what's dx dy, it's always going to be the upside down. And that's something we'll look at more in semester 2. But I want you to appreciate the fact that dy dx can be treated like it was a fraction. So dx dy is just 1 over dy dx. Yes?
Would you recommend to find the answer of dy dx and flip it?
Yeah, well you see, actually, it depends on the situation. I'd say, for this question and for this semester, both methods are fine. But in the next semester, you would definitely find it and then flip it, rather than rearrange it. So for this semester, it doesn't really matter which. The next semester, it will matter. Okay, so write that example down. You wrote that down? Okay, so which ones to do? No. This is way too important. Shh. Right. 1a. What is the derivative in 1a? Look at 1a there. Tell me the derivative. Look at it, tell me the derivative.
56.
Yep, 56 x power 7. What about 1c? 18 e power 9x. Good. It'll take about 5 seconds to do each one, yes? So, I'm sorry, I want all of these done. All of them from 1 and 2. And 1 and 2.
The 1 and 2 later.
Now look, it's not going to take you as long as it seems, okay? Because some of them can be done instantly. In fact, I would not be surprised if some people have them all finished before you go home, okay? And you can do just one from number 3. The last one. Listen carefully. You don't have to do number 4, so delete number 4.
There's no number
All of 1, all of 2, and the last one in 3.
1 from 2, 1 from 3.
For Friday.
Don't forget do you remember this one? We are going to do it with and
There's a lot of Friday.
Your time management is your problem. I gave you lots of time to do it, okay?
for Friday we go to our system.
Really?
Oh yeah. On Mondays.
I'm on Tuesday, and you'll have no excuse not to have it on Tuesday, okay?
We have assignment.
See this? Doesn't care.
On Tuesday we go.
Right. Alright, now working on Right. Hey, look! Seriously, if you work fast, you can get them all done in the next 10 minutes, so snap to it.